Maneesha will tell us about mapping the phase diagram of QCD via fluctuations. Over to you.
Thank you, Prasad. Good afternoon, everyone. Thanks again for giving me this opportunity. Okay, thanks. So today I will continue talking about what I was talking about yesterday, the mapping the hadron quark phase transition. And today I'll emphasize on fluctuation observables relevant for QCD. In particular, I would be focusing on a procedure to convert hydrodynamic fluctuations into correlations of particle multiplicity in momentum space. So this is based on this work, and I'll also, in the second half of the talk, talk more about the work in progress and the ideas that are remaining out there. So to begin with, so we are interested in the emergent phenomena in QCD. As I discussed yesterday, two of the defining properties of QCD are asymptotic freedom and confinement. So we would like to know how these fundamental properties of QCD dynamically emerge in a many-body system governed by QCD interactions. In particular, we are interested in understanding the nature of these phase transitions, and also a very important question that is somewhat intimately tied to these kind of investigations is there a form of hadron quark duality that connects the low temperature and high temperature regime? Two of the complementary approaches that we have today are lattice QCD and heavy ion collisions to study QCDs. So as I showed yesterday, so lattice QCD tells us that at very low temperatures less than 160 MeV, the agreement between hadron resonance gas model and QCD is pretty impressive. Let me remind you what hadron resonance gas model is. It's a model of ideal non-interacting hadrons, including all resonances. The only interactions in this model being mediated by the decay of the resonances. So it's, as I was emphasizing it too much yesterday, it's pretty impressive that it works all the way till about 160 or even 170 MeV, what you call as agreement here. So this was the equation of state, that is pressure, energy density and entropy densities properly normalized by powers of temperature. But if we look at the susceptibilities, that is the second, fourth and sixth order derivatives of pressure with respect to baryon chemical potential, you can see that the hadron resonance gas model prediction given by the pink lines in each of these curves begin to deviate at much lower temperatures. So the disagreement between these two calculations, the actual lattice calculation and the free gas of hadrons, seems to be more evident in higher order susceptibilities.
Why is there, in these first plot, why is there a band? Why is it not
the yellow one?
In the first plot itself, the red, green, blue?
Yeah.
So why is it a band and not a line in this first plot?
I think to account for the uncertainties in the lattice calculation.
Oh, this is also lattice calculation?
Yeah.
Even though there's, this is in temperature axis. Oh,
Yeah.
So this is all zero to chemical potential?
Zero chemical potential, yes. Yeah. So as you see, yeah.
This is the same plot that I got last time. So I think it is basically the flattening is the thing that gives you the consistency in Stefan Boltzmann.
Yeah, if you flatten to the non-interacting limit, yeah. So there are deviations from HRG which become evident at higher order susceptibilities.
And if you already said yesterday, what was on the y-axis, the first plot?
So this has three things. So
Pressure, energy, and
all three things which become the same in the non-interacting limit. So with this, so we also discussed that cumulants of thermodynamic density fluctuations are proportional to generalized thermodynamic susceptibilities in equilibrium, and which means that key to understanding the emergence of strongly coupled QGP from weakly interacting hadron resonance gas somehow lies in these fluctuations, higher order fluctuations. Now let's look at the other approach that we have to study QCD, which is the experimental approach. The QCD terrestrial laboratories we have are heavy ion collisions, and what heavy ion collisions measure are the final particle multiplicity distributions. What these observables tell us is about the state of the matter at freeze out, that is the space-time hypersurface where the system was in equilibrium for the last time before the hadrons freely stream to the detectors. So what you see here is a plot which shows the agreement of the mid-rapidity yields for particles, various particles with the statistical hadron resonance gas model. We can also say that there is one particular temperature and chemical potential describing the yields of each of these particles from pions to higher hadrons, higher mass hadrons. But now the question that we can ask is, what about the event by event fluctuations? Do they also agree with the equation of state as well as we see here?
What does GC stand for?
Where did it?
GC.
Oh, grand canonical ensemble.
So this is, okay, then just to understand, again, this is a complete equilibrium.
Yeah.
And when you say fluctuations, what you mean is, what do you mean when you say fluctuations? Like in the,
These are the mean values.
for a huge set of productions.
Yes, I mean event by event fluctuations. So in every event, different number of particles are formed. So.
Also, I mean, this is a small thing. So I just asked, yesterday you said something about when the root S is large, you can probe chemical potential. That sounds vaguely plausible, but why is there can you explain a little bit more?
So if you have higher energy, so you start with a system which is very baryon rich, highly baryon rich, right? You collide two protons. So if you have higher energies, you can produce more anti-baryons, and therefore your chemical potential decreases because average baryon density decreases. So, yeah.
When root S decreases, you're going to higher chemical potentials.
Sorry?
When root S decreases, you go to higher chemical potentials. When root
Yeah.
S increases, it's effectively zero chemical potential.
Yeah, so that's what I was saying.
But that's what she said, but I thought what she said yesterday was that the root, so you had a bunch of vertical lines.
Yes.
Right? So
Yeah.
I thought the root S increasing was the direction in which the chemical potential. That's not the case.
No, that's not the case.
This way is the.
Yeah.
So when energy is higher, also the argument is you can produce
Yeah.
anti-ions as well.
Yeah. Thanks. So if you see any deviations in the event by event fluctuations from a quantum gas of hadrons, then this can be due to some non-trivialities in your equation of state, such as presence of critical point or some other enhancements due to this transition in the degrees of freedom. Or it can be due to non-equilibrium effects.
Plots of the parameter values of the ensemble.
Yeah, as a function of collision energy. Yes. So this was for one particular collision energy. This is the parameters for the whole collision energies. So
And also one more question. Sorry that
No.
I'm loading a lot of questions. I don't want to say anything.
no, it's fine.
So when you talked about these cumulants,
Uh-huh.
so the point would be that, so since you said that the QCD critical point you expect to be in the Ising model universality class, so the cumulants should also be in that. There's a standard prediction for all of them, correct?
Yeah, in equilibrium. I mean, at least the standard prediction, but there are so many non-universal parameters which change how things look like, but the
Like what? I mean, if the universality class is fixed, then all of them should be fixed.
I'll show you how it differs in a while.
But it's
The power loss will be the same.
Okay. But you're saying that the cumulants can all be controlled by many other parameters. Is that the statement?
You can modify your variables mu and t in such a way that you get exactly what you see in the Ising model, for example.
Okay.
But yeah. So yesterday we saw these plots. These were the factorial cumulants for proton multiplicities from the beam energy scan. And as I mentioned, non-monotonic deviation of cumulants of proton multiplicities or in general particle multiplicities are characteristic signatures of the critical point. So before we look more into this data, I will discuss what we are going to do to have a model that you can use to analyze this data and constrain the equation of state near critical point. So as I mentioned earlier, factorial cumulants subtract the trivial self-correlations in a gas, thereby showing you the genuine multi-particle correlations that are sensitive to critical point. So today I will be focusing on this procedure on how to convert hydrodynamic.
So you showed this yesterday also.
Yeah.
So some of the data points are in these boxes in the empty whatever dimensions. So they don't agree with each other. Right? Say yeah, exactly. Say where your mouse is. What is the reason? Are they different things?
They don't agree means the blue line does not agree.
No, forget the theory. The blue line is the theory. I'm talking about the data points.
So this is what we think is a signature of critical point emerging.
No, the red points are the empty diamonds, right? They don't agree.
Empty red points and then empty diamonds. So one is protons and the other is antiprotons. Factorial cumulants of antiprotons. So yeah. So we need to have some procedure to convert these hydrodynamic fluctuations into correlations of particle multiplicities. So we assume that there is a freeze-out hypersurface. There's a space-time hypersurface where the system is in equilibrium for the last time, and beyond this, the particles just free stream to the detectors. So now we want to determine what the distribution of particles are on this particle multiplicities are on this space-time hypersurface where they interact, where there were interactions, any kind of interactions, elastic or inelastic. So this is a somewhat non-trivial problem and I'll discuss why it is. So in order to go into the details, I'll have to introduce some notations. So this is just a schematic picture of the phase diagram, two-dimensional profile. This is the transverse radius from the center of the fireball, and T is the time in the lab frame. And this blue line which you see is a schematic freeze-out curve, ds mu being a differential element on it and this being a normal at that surface, at that point. So on this surface, you have two equivalent descriptions, one in terms of hydrodynamic variables. So you have the conserved densities, energy, momentum and all conserved charges. You also have information about the correlation functions of each of these all possible combinations of these conserved densities, which I denote by H. So if there are two subscripts, it means it's a 2-point function. The number tells you basically what point function I'm talking about. And AB can be either energy density, momentum density or any of the charge densities. So you're considering all possible correlation functions here. On the kinetic side, you have particle distribution functions, but these have a mean value and you also need to consider their correlation functions like this. So I'll denote the correlation functions of hydrodynamics by H and hydrodynamic variables by H, and correlation functions of particle multiplicities or gas species multiplicities by G. Small letters for hydro indices, energy, number, density or whatever, and capital letters for the phase space properties of the particles and the quantum numbers of the particles themselves. So at freeze out, both these descriptions should agree with each other. You have more degrees of freedom in the kinetic description than in the hydrodynamic description. So whatever hydrodynamics tells you has to be matched with what you get in the kinetic description. So you can calculate average energy densities in the kinetic description by summing over the energy of all particles, and you have to also sum or integrate over the momenta to consider all particles. Similarly, you can do energy densities, number densities by integrating over the phase space and multiplying by the corresponding baryon number. You can also continue doing it and write equations for correlation functions of hydrodynamic densities. But what I want to emphasize here is there are finite number of equations because there are finite number of conserved densities, but there are infinite number of unknown variables because these distribution functions are functions of phase space. So there are infinitely many solutions for this kind of problem. So what freeze out prescription does is to choose one such distribution, hopefully the one which is the most probable one, and maximum entropy principle provides a natural and a consistent choice in this.
Like the small p mu and q are just momentum and the number.
Yeah, thanks. Yeah.
So maximum entropy principle will be somehow maximizing entropy for these FAs. Is that right?
Yes. So yeah, so you'll get many solutions, but for each of these solutions, then you can see what's the maxima for each of the particle distribution function, and then maximize it basically. The solution is the one which maximizes the entropy of the fluctuating ones.
So here's the question.
Yeah.
So you're expanding gas, right? So
Yeah.
should the entropy density, not the entropy. Small is
That is right. Yeah. So you have a volume. So each fluid cell has a volume.
probably asking the entropy density.
I think I'm maximizing the entropy, because you always look at definite volumes, fluid cell volumes. So.
So deep inside the firewall, the system has thermalized, and so you can model it by
Hydrodynamic.
canonical or non-canonical answer. But at the edge, which is where you're interested,
Uh-huh.
where at that edge,
Yeah.
can we say what kind of an ensemble it is?
Yeah, so that's what we are trying to find out by, so it won't be, the gas won't be produced in equilibrium because there are out of equilibrium correlations in the hydrodynamic system. So you need to match with those. So the gas that is produced will be out of equilibrium.
I see. When you say gas, the gas outside is what you call the hadron gas,
Yeah,
and whereas inside the firewall is QGP.
yeah, hydrodynamic system. It can be hadrons as well, but you just know information about the hydrodynamic densities. Did I discuss this? Okay, yeah. So maximum entropy is not a new thing even in this field. So there is a standard freeze-out procedure which is called the Cooper-Frye freeze-out, which has been in use for like 50 years. This essentially coincides with this principle of maximum entropy. So in this case, you have just a hydrodynamic system. There are no fluctuations. So you ask, so what's the average particle multiplicity that comes out from this given conserved densities, right? But that also has infinite number of solutions because there are only few equations corresponding to each conserved densities. Then you are left with the same kind of problem. So then you maximize the thermodynamic entropy of the gas. That necessarily means that your energy density and number density just correspond to the temperature and chemical potential of the fields, of the hydrodynamic fields there. So that is also what sometimes people call as the statistical hadron resonance gas model. And this is the agreement of that model for Alice energies, and you can see that the agreement varies over 9 or 10 relative orders of magnitude. So it is good for pions as well as particles such as helium nuclei. So
this is again the average.
this is just again the average. So they didn't have a prescription to freeze out fluctuations. Because initially you didn't need that, you were just looking at the average yields of particles, or 1-point functions essentially. Recently there was also some inclusion of viscous correction into this framework, again for 1-point functions. And this was where we got the motivation to actually use this maximum entropy freeze out procedure to freeze out fluctuations. So the question that we were asking is just this. So given all the information about hydrodynamic densities on the freeze out hypothesis and this is the only information that you have about the system at the freeze out hypothesis, what is the least biased ensemble of free streaming particles that you can get that agrees with your hydrodynamic description? That essentially means that you choose that distribution which maximizes the entropy of your fluctuating particle ensemble, subject to these conditions of matching from hydrodynamics. So, in the equilibrium, when we were considering the freeze out of like just one point particles, we just need to maximize the thermodynamic entropy. But when you have the correlation functions out of equilibrium, you need to think of an entropy, a Gibbs entropy, which is more general. So you may think of Gibbs entropy as a functional of the mean densities in your system, mean conserved densities in your system, or equivalently you can think of it as function of the probability distribution for these particle distributions, probability distribution for the F's, which are the particle distributions themselves. So this you can write as the equilibrium entropy plus something called the relative entropy. So maximizing this relative entropy just means that you're taking the system as close to equilibrium in some sense, because you don't know anything about anything other than the hydrodynamic densities. So that's exactly what we are going to do here. So here S is not just a function of F bar, the mean densities, it also becomes the function of the 2, 3 and higher order correlation functions. And you will minimize this functional with respect to each of these variables to, and also impose the condition.
F bar, you would go back to the Friday or whatever.
Yeah, you would go back to Friday. Yeah, and also, so this is the thermodynamic entropy, S0. So if all but the 2-point correlations are in equilibrium, you can get a closed form solution for this entropy as a function of G, and that's what's written here. This function is structurally analogous to the two-particle irreducible effective action, which is commonly used in quantum field theory. So we call this two-particle irreducible entropy because it has the same form. So here this S0 is the thermodynamic entropy, the equilibrium entropy, and this function, if you plot it, you can convince yourself that it's a strictly non-positive quantity, meaning that S2 is always greater than, less than or equal to S0. The entropy is always maximized in equilibrium, and only when G equal to G bar being the equilibrium 2-point function, this quantity actually becomes S0 and is maximized. So what we need to do for the maximum entropy procedure is to maximize this S2 with respect to G, that is solve this equation, find the stationary point, and that gives you G, and also subjected to the matching condition that will allow you to get a solution for the 2-point correlations on the freeze out hypersurface for the particle multiplicities.
This relative entropy is the same thing for information theory.
Yes. I think so, yeah. I forget what KL is, yeah, but it has more than one name. KL divergence is one. What we see here is that this is a linearized form. You can actually get an exact solution for 2-point correlations. So delta G is just proportional to delta H. Delta meaning, so this subtracts the equilibrium contribution in the gas, and so whatever out of equilibrium correlation in gas is just equal to out of equilibrium fluctuations in the fluid times some factors which are related to the quantum numbers and kinematics of the distribution. So you can continue doing this kind of program and then find that the 3-point correlations are proportional to the of the hydrodynamic 3-point correlations of the particle multiplicity can be found to be proportional to the 3-point correlations of hydrodynamic densities. But now this measure which we call this delta hat is very different from delta or even the total correlations. So these are the irreducible relative correlations that come at that order. So if you look at the total correlations either in the hydrodynamic case or in the gas case, there are 3 distinct contributions. One comes from the equilibrium form of the correlation function in the gas. Then there are some non-trivial correlations which come due to the lower order 2-point correlators. And then there is this term which cannot be written in terms of lower order correlators. So this is what we call the irreducible relative cumulants. And in terms of these irreducible relative cumulants, finding the freeze-out solution is somewhat very easy. They're just proportional to each other. So what these irreducible relative cumulants give us is the non-trivial correlations that arise at each order. And if you integrate these over the phase space of the particles that are produced at freeze-out, what you get is the generalized factorial cumulant. Why do I call it generalized? Because as we mentioned earlier, factorial cumulants subtract the trivial correlations in the Boltzmann gas. This gives you the non-trivial correlation with respect to any reference distribution function. So even if you have a Fermi gas, for example, there are some non-trivial correlations coming due to the quantum statistics. This allows you to subtract that and get the non-trivial correlations. And that's not just for a quantum gas or Fermi-Dirac or Bose-Einstein. You give any reference distribution, you can find the non-trivial correlations at that order. So this novel correlation measure, what we call as the irreducible relative cumulant, is somewhat useful, I think, even in understanding how the correlation functions in the QCD deviate from the correlation functions in hadron resonance gas. So this will probably be helpful. So in constructing models, hadronic models, that can reproduce the lattice QCD results, and also if necessary the PQCD results. So you have a hadronic model that can actually, you probably have, I have not tried this out, but this is just an idea that I'm thinking of working on. You'll have a hadronic model which can describe deconfinement, although the degrees of freedom in the model are not just hadrons, you can still describe deconfinement because there's a way to construct it naturally using this procedure. So that was for lattice QCD. But if you look for heavy ion collisions, so now we have a freeze-out procedure telling you if you know the hydrodynamic correlations at freeze-out hypersurface, what should be the corresponding correlations of particle multiplicities in momentum space. So delta G hat is a function of the phase space coordinates of the particle multiplicities, particle species at freeze-out. So we want to use this now for applications to heavy ion collisions. The first one is what it was intended for when we actually made it, critical point search. So what we are planning to do, and we are in the process of doing, is the following. So we start with a tunable family of equation of state which can describe the QCD equation of state near the critical point. So it's an infinite family of, it's a parametric family of equation of state which can always describe the QCD equation of state near the critical point. The applicability of this regime may be different, but this is somewhat like a universal class that you can construct using some universal properties. And then we want to use these universal equation of states and evolve it using some dynamical description for fluctuating hydrodynamic fields, and then use this freeze-out procedure to convert these hydrodynamic fluctuations at freeze-out to cumulants of particle multiplicities. The second application is to get an equilibrium prediction for cumulants of particle multiplicities from lattice QCD. So traditionally, when we think of lattice QCD and heavy ion collisions, they are somewhat complementary in the sense that, not complementary, they look very different because the observables in heavy ion collisions are not thermodynamic variables, and in lattice QCD you do not have quantum numbers for like these protons and other particle species that you're interested in. So it seems like lattice QCD can never determine these particle multiplicities from theory directly, from first principles directly. So what this maximum entropy and such gives us is a procedure to convert the lattice QCD susceptibilities into observables such as factorial cumulants of particle multiplicities. So this is a work in progress, and we are seeing some good signs, but it's still a work in progress, so not ready to publish on it. So, coming to the first application, which is the critical point search. So, let me remind you, our goal is to put bounds on the location of the critical point and constrain the equation of state around it, given the data from heavy ion collisions.
By location, you mean T and V?
Yes. So, location, yeah, in the T mu V plane. So, the equation of state of QCD in your critical point in general can be written like this. So, very close to the critical point, singularities of the equation of state are given by the 3D Ising model. That's the universality of critical phenomena, where these Ising variables R and H are the reduced temperature and magnetic field, and they are mapped to the QCD variables chemical potential and temperature via an analytic mapping. To describe the leading singular behavior, it suffices to use just a linear mapping between the variables. And then you can construct these background normal or subleading singular equation of states so that you reproduce whatever else you know about QCD at different limits.
How do you know that map? So essentially you're saying that this picture on the left gets mapped by something into the picture on the right.
Yeah.
Correct?
Yeah.
So that means that like your, the crossover region or something which will be kind of like a sort of a divergent from that thing on the right of this picture, I guess. Right? It will be a little bit like, some region which is crossover.
Yeah.
That will get mapped to some other thing over there.
Yeah.
So, but if you don't know, you said that you don't know the map.
Exactly.
Exactly. So, then it's always kind of lost.
That's the point, right? So, we don't know what the map is, but to describe the leading singular behavior, it suffices to use a linear map. You can improve it systematically by improving your analytical map, but to start with, you start with a linear map. For linear map, you need just a minimal amount of parameters, 2 for the location of the critical point, 2 for the angles that this magnetic field and reduced temperature make on the mu T plane, and then 2 scale factors, which for now I call rho bar and W, to determine how this H and R scale on this T mu plane. So, with these 6 non-universal parameters, you have a parametric family of equation of states, which you can consider.
That's the answer to my earlier question, which was that, so these 6 parameters are the freedom that you have in relating the cumulants to the universal.
Yes, exactly. Yes. Yes.
Sorry, how convinced are we that the QCD critical point is qualitatively very much like the
Ising model.
3D Ising model, critical point?
So the conviction is just based on, as far as we know about QCD, there are no real symmetries for physical quark masses. So it has to be in the Z2 Ising universality class.
How do you mean there are no real
symmetries that get broken at this stage? So if you look at what symmetries are really, so there's no difference. At this critical point,
the analogy somehow is that the quark-gluon plasma versus hadrons is the analog of water versus water vapor.
Yeah, so at critical point they just become the same. So that's the only emergent symmetry there. So this is Z2 symmetry, 2 states becoming similar. So yeah, but you're right, you can have some influences from the chiral limits because of the smallness of the quark mass. But that does not change the universality of the equation of state. What that changes are the non-universal parameters. So close enough to the critical point, it will have essentially this kind of form, if what we think we know about QCD is right.
Presumably one could have, I'm not suggesting that I do this, but one could have looked at some other model instead of the 3D Ising model and tried to map that one. So
yeah. Yeah, so there is no way we can.
Not do that?
It's not really the simplest. That's not the reason. The reason is more that there is like.
Saying that, but it also happens to be sort of simple.
I don't think there's a big difference if you look at like ON models or Z2 models. The equation of states are similar. Like.
But I mean, if you have critical model,
might be. It might become actually even easier, right? Yeah.
So because that's kind of more like your chiral limit.
To start with, so we just take this tunable family of equation of states and forget that there could be critical slowing down, and just use the hydrodynamic correlations, equilibrium values of these hydrodynamic correlation functions that freeze out, and see what we get for the cumulants of particle multiplicities. So this is just for an arbitrary equation of state from this family of equation of states. So I have chosen some parameters and plotted the second, third and fourth baryon susceptibilities. These are contour plots, red meaning negative regions and blue meaning positive regions. And on the lower panel what you see are the observables, the factorial cumulants, second, third and fourth for proton multiplicity. And the white curve here is the freeze out curve. So as you go along this, you see these are the values for the what is that called, the cumulants, factorial cumulants that we get. And there are three curves actually, so we actually also varied the distance of this freeze out curve from the phase boundary. This was, sorry I should have mentioned, this is delta TF equal to 4 MeV and this is 9 MeV. So if you go from 4 MeV to 9 MeV, you can see that, say in these cases, you can see that it falls by an order of magnitude. So uncertainties in your freeze out curve itself can cause a lot of smearing, which also should be accounted for in real calculations. So the other things that we learn from these are like how these different parameters affects different features of these curves. For example, we could learn that this rho bar is essentially responsible for fixing the shape of these curves, and W just rescales these numbers. And there's also this difference between alpha 1 and alpha 2, which also plays a role in determining the shapes.
So those parameters that you listed, those 6 or something parameters, those are what control the shape of it. Is that correct to understand that?
So this is the equation of state. Equation of state is specified by these 6 parameters.
Right.
Now I'm saying mu c and Tc, if you just say the location, these curves just shift in some sense, right? So the shapes are determined by this parameter rho bar and alpha 1 minus alpha 2, and W just rescales these numbers. So yeah, you can do this for all equation of state. Rho bar that determines the shape in equilibrium. So dynamics can change shapes also. So now we then decided to use some lattice QCD calculations at imaginary chemical potential and extrapolating it to learn something about these non-universal parameters. So there is this Liang theorem which tells that the Liang singularities of the Ising model lie along the imaginary h axis, and when you take h equal to 0, essentially this line of singularities pinch the real axis at the critical point. So we use that universal theorem to basically extrapolate the Liang singularities that you get from your imaginary chemical potential to real axis and determine the, I shouldn't say we, this was Gopche's work, to determine the location of the critical point as well as the slope of the first order curve, which is alpha 1, the tan of alpha 1. What we did further here is to show that you can also find the factor rho bar which controls the shape, and you can put some bounds on this rho bar based on for different values of alpha 2. So this kind of calculation from lattice actually helps you to constrain some of the parameters. Now the only unconstrained parameters are the difference between the angles alpha 1 minus alpha 2 and W. And there is this nice feature in the chiral limit that when you go from this Z2 critical point to the tri-critical point, your universality goes from phi 4 universality class to phi raised to 6 universality class. And in this limit, we find that this Ising axis actually goes to 0 exactly at the phi raised to 6 point. So therefore, this difference between these angles actually scale as quark mass raised to 2 by 5, where 2 by 5 is the tri-critical exponent. Okay, so this was about equilibrium properties. Now, as I said, there is always critical slowing down. Away from the critical point, we have seen evidences of hydrodynamics being able to describe a lot of what you see in the experiments. But as you get closer to the critical point, if at all it exists, then you would expect to see these critical slowing down or different modes actually falling out of equilibrium, and you need different dynamical equations for describing the evolution of these correlation functions of these slow hydrodynamic modes. Close to the critical point, the way in which these modes fall out of equilibrium is also somewhat universal. The mode that falls out of equilibrium the fastest or the slowest non-conserved mode near the critical point corresponds to this correlation functions of this diffusive mode, which is called the entropy per virion. Entropy per virion is just diffusive, it goes as it does not propagate, it goes as k squared, and the relaxation rate for that essentially goes as correlation length to the power -3, meaning at the critical point this becomes 0. There are also other hydrodynamic modes which fall out of equilibrium, but the relaxation rates are parametrically much smaller than this. Therefore, the first one which you need to consider is this diffusive mode, and if you get even closer to the critical point, then you can think of also including shear modes. So this is a calculation where we look at how the Wigner transform of the slowest mode evolves as a function of time while the fireball passes close to the critical point. So there's an expansion trajectory which sort of moves close to the critical point as the temperature drops down. So here on the x-axis what I've shown is the temperature along that trajectory, and the dashed curves are the equilibrium predictions for those hydrodynamic correlations. And you can see the thick black curve, which is the actual correlation function, kind of lags behind when you look at how it evolves. So there is a delay in the rise of this peak compared to the equilibrium peak. You can also see that the magnitude of this, the maximum here is much lower than what you see in the equilibrium scenario, which is a consequence of conservation. Again, another consequence of critical slowing down is that it takes longer to fall back. So although the equilibrium correlations have actually fallen back, the out of equilibrium correlations still remain to be larger than the equilibrium value at freeze. So since freeze out actually happens much later than the phase boundary, passes through the phase boundary and then falls out of equilibrium. So it is possible that the actual value that you have for the correlation function at freeze out is much larger than what you expect from equilibrium predictions. So this kind of effect is somewhat known as, commonly known as prolonged memory of the critical point. So here we have actually done just like these dynamical model calculations with very simplistic systems. The thing which we want to do is do such a thing for like this parametric family of equation of states. The relaxation rate also introduces a new dynamical parameter here, which is essentially the scale of the correlation length in the system, which is also non-universal in some sense, which you cannot get from the universal properties. So dynamics adds one more non-universal parameter to the list of non-universal parameters that we want to constrain.
So, maybe I'm a couple of slides behind, but
sure, thanks.
No, you don't have to go back. So this picture that you described, where you have a hadron gas on outside of the freeze-out region and maybe QGP or maybe something else. Is it fair to think of this as the boundary between two kinds of immiscible gases or immiscible liquids?
One is a liquid and the other is a gas.
Yes.
Immiscible.
Immiscible in the sense that they have very different properties.
That's true.
That's the only sense in which I use the word immiscible. But otherwise, two very distinct kinds of fluids.
So this this way of constructing this freeze out hypersurface is somewhat very ad hoc, right? So you think that it actually happens at one freeze out hypersurface. In principle, you could have like a shell of region where things change.
That
So
phrase that you used reminded me of boundary layer theory that is used all the time by fluid mechanics. So there's a very thin layer.
Mm-hmm.
And I think it's when the fluid is flowing past the boundary. Here it's radially expanding.
It's radially expanding.
And also, it seems to me that this is a particular after a certain time that happens. And it's not at the, if you're talking at some point at a cross section or something, it's sensitive.
Yeah, but a lot of the work, if I understood correctly, is assuming that we're looking at a particular point of time or looking at time scales which are.
I don't know.
can you say that again? Lot of work.
It seemed to me that a lot of the discussion is about at a particular point in time, or at least on time scales that are very different from the time scale over which.
Microscopic terms.
Yeah.
Okay.
No, never mind. Maybe we can continue. I can ask you later.
Okay.
So my picture was that, I mean, so it's like, I had no idea, but my picture was that the collision happens and it expands, and at some certain time it hadronizes, right? So at that time is there really an interior for the quark-gluon plasma, or is it like at that point okay, I'm kind of thinking probably there was just one collision. Maybe there is like a collision is happening anonymously.
No. So you are always thinking of one collision, but one collision also is not just one point.
Right,
so you have different fluid cells and you have temperature gradients all over.
That's fine too. That's kind of like a pancake type of collision as well. Is that correct?
Yeah.
So and then but I'm saying that the hadronization happens after the collision has happened after a certain time in some sense. So is there an interior quark-gluon plasma even when the hadronization is happening?
Yes. The reason being not all points in the fluid cell freeze out at the same time. So this when I was plotting.
That's kind of complicated.
No, that is a crude picture that I had in mind. There is something like the quark-gluon plasma or whatever, and then there is the hadron gas outside that. For at least for a sufficiently short length of time, we can think of these as two kinds of fluids with a fluid boundary, two completely different kinds of fluids.
True, yes.
And so this kind of picture, if I remember my undergraduate fluid mechanics, is modeled by a very important part of modeling this kind of situation comes from something called boundary layer theory, where there is a certain bound where you make an assumption about where there is a hypothesis about a very small region of one fluid very close to the boundary, and the properties of that are described by the hypothesis of the boundary layer theory.
So it's different from a two fluid interface just because of the fact that even if you have two fluids, the number of degrees of freedom between the two things are still the same. You still have conserved densities, right? You have a fluid description on both sides. But here it's more than a fluid on one side. You have microscopic degrees of freedom in some sense because you have information about each particle species, right? So in that sense it's different. So I think in your case you can have few equations and there's number of solutions for that. I remember, are the same. So you can just solve for it based on the boundary conditions, and right? Is that what you're saying?
No.
Okay, thanks.
But I think the strongest criticism of what I was thinking maybe based on what Prasad said, that they are not moving with respect to each other like this. They are moving, most of the motion is expansion outwards rather than gliding across each other. So it may not even be useful.
Okay. Where was? Yes. So basically, what we are aiming towards is to just have this like universal framework, which has a family of equation of states with the critical point, correlation dynamics, which is also just based on the dynamic universality near liquid gas like critical point, which is often called as model H in the literature, and also fluctuation freeze out prescription, which is somewhat based on a universal principle maximization of entropy. So that gives you a minimal parameter set which has like 7 parameters, and we are hoping to constrain these parameters by doing a Bayesian fit of multiple beam energy scan observables, not just the factorial cumulants of proton multiplicity, but also other particle multiplicities and mixed cumulants as well. So beam energy scan has now almost taken data, and they are just still analyzing it, but there is no more runs to be conducted anywhere in the near time. But we have new colliders coming up in the lower energy collisions. The most important one being the CBM1, which spans a freeze out region in chemical potential from 500 to 800 MeV. This is much better than RIC in some sense because it has higher luminosity, statistics and interaction rates, and this is supposed to be built as a fixed target program, unlike RIC, which was basically intended to be a collider project. There is also some new things, as in you can collide variable nuclei with different isospin contents, so you can also probe the finite isospin region of the QCD phase diagram. We also have access to new variables such as dielectron spectra, which allows us to probe new kind of physics that we haven't done with the cumulants observers yet. And one other important thing about this colliders, CBM collider, is that it lies in the optimal range for hypernuclei production, and this is one of also the open problems that we will discuss.
So all those are planned, or some of them are already working?
So these are all working, and HADIS is also working, and FAIR is planned and approved, and there are these dots which are proposed but not approved.
Like DICE,
Yeah, JPark and I think DICE, Na60 plus. I think they are proposing some improvements or some new energy ranges or something. Yeah, this is not Na60, this is Na60 plus. This is not Na60, it's Na60 plus. So there are also some interesting features that come in the first order regime due to the presence of a critical point. In particular, you see that the hydrodynamic trajectories, which in the zeroth order limit are just adiabatic entropy per baryon constant curves, isentropic trajectories. You see that there is a lensing behavior that happens close to the critical point. And it's possible to explain this lensing behavior by looking at some universal features near the critical point. In particular, this is related to a very simple feature that we see near the critical point. Maybe I can explain this. So this is entropy per baryon plotted as a function of Tc minus T by Tc. So this is the temperature difference from the critical temperature. And the lines here are the entropy per baryon along the first order line. So this is one phase, and this is entropy per baryon along the other phase. So one thing that you see here is that because of universal scaling, you know that the entropy per baryon along each of these phases, one should approach from below and the other should approach from above. So in principle, you can show that this goes as T minus Tc raised to minus beta with a minus sign in front. So it should come with different. This one? These are entropy per baryon equal isentropic contours. So adiabatic trajectories.
And these are sort of experimental things.
Which one? These
The
ones?
next ones.
These are some simulations. Yeah. Yeah. Next
So
one.
simulation, how many do these simulations? What the simulation of what are the
This is hydrodynamic simulations. Hydrodynamic trajectories close to this.
So with some particular equation of state and so on.
With some particular. In the presence of a critical point, you see these kind of things. So it has a critical point. So
The
yeah.
numbers that you or your collaborator found, if I remember, temperature was around 90 and the potential was 500 something. So,
Oh, this was just some model thing which they did much before that.
much before that.
Yeah.
Yes. It's 2005.
This one I think is from 22, but the other one was 23. So slightly different. Not much.
Before.
Slightly before that. But yeah, I guess. It's okay to play around with the numbers yet, because since we don't know the equation of state, and since if you're just looking at the critical features, universal features around it, moving the critical point is just like moving it in phase space. So you don't.
But if you're only playing around with it, then it makes sense pictures. But
Yeah.
at some point, it will be useful to something.
I think this is at least a qualitative feature you can see here. I mean, that's the message maybe.
Yeah. So yeah.
That what there is a critical point. So things are going to be messy anyway.
So I'm a little surprised by so is there even when there's a critical point you can do hydrodynamic simulations there? Is that there is
Some of the constants get actually renormalized and stuff, so you can actually apply hydrodynamics for describing just the average properties to very close regions, but I think ultimately it would break down because gradient expansion is more useful.
ultimately that
But how so we are so that's something, that's a limitation of everything that we do. We cannot, of course, like only if the system is close enough to equilibrium can we probe anything about the equation of state. So we are hoping that and we are doing a beam energy scan, so unless we are like so unlucky, we might not end up being so close to the critical point. Okay, so what I wanted to just say here was that so here at the critical point, there's a universality which tells you that this should be the behavior. It should be higher than the critical entropy in one of the phases, and for the other phase, the entropy per baryon should be less than the entropy per baryon at the critical point. And you also know that at t equal to 0, these first order lines should approach the same point, because entropy becomes essentially 0 at that critical point, at that point, and this you expect to see such a shape. So what goes up has to come down, and in this you can see that if you have an adiabatic curve here, which are just horizontal lines on this, one which goes through the with an entropy per baryon more than the critical entropy would hit it as one phase and then come out as the same phase. So it has seen the first order region, but basically it has not seen the change of phase if you look at the initial and final states. And this has implications not only for heavy ion collisions but also for neutron star mergers, especially for neutron star mergers where the intermediate dynamics does not matter, which spinodal formations and all take at time scales which are much smaller than the scales of observation. So even though there is a first order phase there, we might, even though if there is a quark matter core inside a neutron star merger, we might not actually see any remnant of this if the equation of state is such that, if it's of that scenario. So there is a lot more to do here in terms of dynamics for heavy ion collisions. There has not been much studies on spinodal and nucleation dynamics relevant for relativistic systems. And about fluctuations in this region, it has been almost not at all studied for relativistic systems. So these are things that are planned to be done in the future if you want to study what's happening in the colliders of the CMB and so on. And there is also an interesting question of what happens if the freeze out happens during the first order transient regime. How do you see these spinodal and other formations in the hadronic distributions that you see at the freeze out? So these are all open questions in this field which at this moment we don't have answers to. So since CBM also falls in the optimal range of looking for hypernuclear production, one thing that we would like to understand better is that while it's really impressive that such a maximum entropy freeze-out principle can explain things, average yields of various different particles, it's somewhat incomprehensible to think that there was a free hypertritron in this thermal bath at 156 MeV when the binding energy of this is a few hundred keVs. So this kind of puzzle can probably be solved if we actually are also able to look into the cumulants of these hypernuclei production. To do such measurements, you need very high statistics, and CBM seems to be in the right spot to actually ask these kind of questions and understand hypernuclei production, which is also relevance for like neutron stars where hyperon production is a very big puzzle.
So basically, very crudely, the idea would be that because the non-Gaussianities are somehow what are responsible for this particle being saved.
Yeah. Okay, so I'm coming to the summary of my talk. So the state-of-art lattice QCD heavy ion collisions and neutron star observations provide somewhat complementary approaches to probe QCD. Exciting times ahead, good time to play the middleman and bridge gaps. So another thing that we think is true is probably understanding the emergence of strongly coupled QGP from weakly interacting hadron gas lies in our understanding about the fluctuations in the system. And these new measures, called the generalized factorial cumulants, could guide models of hadron quark duality. So there is a new generalization for the freeze out procedure which also includes fluctuations. There are some unexplored applications of this to early universe cosmology where also you have a freeze out scenario, and if you want to look at fluctuating relative abundances and stuff, fluctuations in the relative abundances and stuff, perhaps there is something to do here. And one important unsolved question in heavy ion collisions is why hydro works so well for small systems. So one thing that we haven't ever explored here is what about the fluctuations. In fact, it is the fluctuations which tells you like how different it is from a hydrodynamic system. And maybe you can use this procedure to say something about the observables in these small systems.
You say small systems, what kind of is typically the particle number?
So when I think of small systems, I'm thinking at least one of these is a proton or both of them are protons.
That's all.
That's all. I mean, even these systems you see.
I mean, apart from the mystery of why hydrodynamics works well, there's a mystery why thermodynamics works.
Exactly. Yeah.
Just few quarks and some little bit of blue.
Yeah, but there is a lot of energy,
That
which
may
is
be,
the reason.
but,
Yeah.
Usually we think of thermodynamics as
Many bodies.
So the valence quarks will be few, but
given that, okay, you can push in a lot of energy, you can pop things out of the vacuum.
and then there could be a large number.
Yeah.
But thermodynamics seems to work even when you tune the energies
That is
down,
yeah.
fairly down.
So something else could also be going on. Yes.
But
You are the systems you look into.
yeah, that's right.
9
Cool.
degrees of freedom.
Yeah,
10, 9, but you still have
6 degrees of freedom or 3. Can get
Cold atoms.
No.
Yeah, I mean, it's a system of 3 particles which
Chaos.
thermodynamics. Essentially because of chaos.
I see.
But you
Oh.
Tell us about your work.
Yes. And then we have this theoretical framework ready to constrain the critical point and the equation of state near it using data based on a universality principles, based on universality principles. And what remains to be done is to do a quantitative analysis so that we can infer something about the QCD equation of state. A lot of things to be done in the first order regime, and experimental programs with FAIR, NICA and HEDIS are in the right time of events happening. So there's a lot of developments actually also happening here. We are working on some things, and hopefully by the time this FAIR and things are ready to be public for taking data, so I hope we have some theoretical predictions for this thing as well. So again, coming back to the question which I was putting forth yesterday, there is a possibility of a critical point in a neutron star from this axial anomaly based considerations, and it may be worth an idea to still look for.
The lower end of the picture that you have?
Yeah.
I was wondering because otherwise the temperature may be too high.
I thought that was nuclear liquid, nuclear gas.
No, so not that. So I was saying about so this line of first order curves that comes from the high temperature critical point can enter some second critical point.
I mean the temperature looks a little too high.
No, there are two critical points at the low end.
Yeah.
The second.
So second one, the lower one might be a little far away.
That Japanese fellow.
Japanese fellow, Hatsuda. I guess, yeah, thank you. Open to all questions.
We had quite a few questions. Still, we have time for a couple of more questions. It's not. So, yeah, thank you once again.
Thank you.